All right, I see you there, Alex. And I see that you're talking, but I'm not hearing you. I must have my sound turned off. Yep, now I've got my sound on. So we'll see if anybody else shows up in a minute. Otherwise, we'll just start and record it and they can look later. We get some nasty feedback if microphones are on and you folks are all talking, so you should be careful with that.
Okay.
All right, we're going to go to Unit 8. I haven't decided yet what to do about Unit 7. I'm kind of wondering, that's because I'm assuming that we're going to be going the rest of the year on this plan. I don't really think that there's much chance of school coming back this year. I hope I'm wrong, but I don't think so. So I'm trying to figure out what to do about Unit 7 in electronics. Right now, I'm wondering about, there's only 4 of you, I'm wondering about mailing a electronics kit to each of you and letting you just work on them at home. Some of you, like Alex, won't have any problem at all. Some of you, like, well, I guess I won't say. We all know who I'm talking about. Some of you will get all frustrated and think it's impossible. And some of you may not even try very hard. But for right now, quantum physics, and we are certainly not going to go into this in any huge detail. I mean, you can get your PhD in quantum physics and still not get everything figured out. So we're just kind of skimming the very, very top of the, this is the creme de la creme, the cream of the cream. Quantum physics is ultimately math. It's a mathematical description of atoms. So we'll start with electrons. And there's all kinds of just weird names here. I mean, they basically are making up names as they go. Sometimes they make sense, like that word wavicle. And sometimes they don't make sense. Like later on, you're going to see up and down and charm as names for particles. So I don't know, it's kind of funny actually in some cases. But electrons are wavicles. They act like a wave and as a particle. The same thing is said of light. Inside atoms, electrons act like waves. Outside atoms, like let's say an electrical current, electrons act like particles. So that's part of the reason we have trouble visualizing what an atom looks like, because we keep trying to visualize the electrons as particles, and when they're in the atom, they act like a wave. So it's almost impossible to visualize. Now, we did talk about quantum numbers in chemistry, so this is a little bit review. Electrons are described by their quantum number. Every electron has its own unique quantum number. Every electron in an atom has its own unique quantum number. So if I had 2 carbon atoms with 12 electrons, that's wrong, 6 electrons. If I had 2 carbon atoms with 6 electrons, in one of the carbon atoms, each of the 6 electrons would have a different quantum number from each other. But in the two atoms, I hope this makes sense. In the two atoms, the electron, the first electron in the one atom would have the same quantum number as the first electron in the second atom. The second electron in the first atom would have the same quantum number as the second electron in the second atom, and so on. So they're unique in each atom. The quantum number is broken down in, and as I told you in 10th grade, by the way, this this number is not a number like a count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is a number like it's a number like a zip code or a phone number, or can't think of any other good examples off the top of my head right now. But it's a number that identifies, it's not a number that counts quantity. So the principal quantum number is the first part of the quantum number. It describes the energy level that the electron is in. There are technically an infinite number of electron levels, not electron levels, energy levels. But in practice, we only worry about the 7 levels that are in the ground state being when the atom is at its lowest energy, and all of the electrons are in their lowest level, because as an electron gets heated, or as an atom gets heated, its electrons jump to higher energy levels, move farther away from the nucleus. Now, people view energy levels as distance from the nucleus. And the way I just said it, they jump farther from the nucleus, makes it sound like that's true, but it's not. I mean, it's not totally untrue. There is a correlation, a rough correlation between energy level and distance from the nucleus, but it's only a rough correlation. In the old days, I just mentioned this in point B, and it's supposed to be used, not us. Some references use letter names for the energy levels. Now, I don't know that I've seen this since college, but some of the old books and some of the old teachers used to say energy level 1, 2, 3, 4, 5, 6, 7, were, if I remember right, it was KLMNOPQ, but I'm not sure I remember right on that. So I just put that there in case you happen to run across it later, so you're not totally confused. Sublevel quantum number describes the eccentricity. In other words, how oval-ish it is, whether it's, except oval is not the right word. Describes the eccentricity of an electron's orbital. There are 4 possibilities. They are called 0, 1, 2, 3. 0, as you see, represents oval, and it's like class. I got to pause to think what I'm doing here. And 0 represents spherical. The others represent increasing degrees of elliptical. So the 0 energy level, and it is very common to, I don't know why I didn't put it there. It is very common to give these letter names S, P, D, and F. And those are used commonly, very commonly. Unlike up here, where they just kind of, as far as I know, have forgotten about them. All right, so S represents spherical, and P, which would be number 1, is imagine an XYZ graph. And it's very hard to draw this three-dimensional on two-dimensional plane, but they are kind of two lobes like this, and I won't get it right. And one goes on the x-axis, and one goes on the y-axis, and one goes, let's see, I should avoid green for red-green colorblind day. One goes on the z-axis. Now, if you can imagine, and that's just a bunch of scribbles, you're going to have to use some imagination here. But if you can imagine, those can be quite, I don't know, what should I say, chubby, because they can expand till they have lots of room to expand. They've got, what would that be? Would that be 90 degrees? Seems like that should be 90 degrees right there. The D gets, which is 2, the D gets to be really, really pretty much impossible. Because how in the world do you draw a 5-axis graph? X, Y, Z, A, B, or whatever you would label them. And okay, this isn't even going to be close. X, Y, Z. I don't even know where to put the next lines. Like this. But that's only, that's only 1, 2, 3, 4. That's only 4. I don't know where the next one would be. I guess the next one must be right there and going back behind. Whatever. You're going to have to imagine, use some imagination here. These level 2, which is the D, are not going to have 90 degrees of room between each other. They're only going to have, I don't know how to figure it quickly. They're going to have a lot less than 90 degrees, 45 degrees, I don't know. And it doesn't really matter what the degrees are. What you need to see is they're getting skinnier the more we pack in. And if you thought that was hard, the third the third sublevel, which is the same as F, has 7 axes on our graph, which I don't even have a ghost of a clue how to draw that. Try to draw that on a 2-dimensional. And I don't have a ghost of a clue what the angles would be, because remember, not 2-dimensional, 3-dimensional. In 3-dimensional, we're looking at angles different. It's, is it 4 pi radians instead of 2 pi radians is what the total is. So all I really want you to understand right now is that the sublevel quantum number describes the eccentricity going from spherical to more and more elliptical, but don't think ellipse like this, because they pinch at the bottom because all of the different orbitals have to fit in between each other. I think that somehow there's a raise your hand option here if you have any questions. At least people were using it yesterday when I did this. Now, the magnetic quantum number is not used very much at lower levels of chemistry. It just describes the 3-dimensional orientation of an electron's orbitals. In other words, it tells, if we can go back to a simpler version of our picture here, In other words, we'll go to the simple one, the P, which is just XYZ. So we have one orbital here, and I'm doing a crappy job of drawing them, and another orbital here, and another orbital here, and another one here, and XYZ just tells which one. I mean, the magnetic quantum number just tells which one. So we pick one. Doesn't matter which one we pick. We pick one, and we call it 0. And it really doesn't matter which one we pick. This is just a relative to each other number. So whichever one you call 0, the other one is number 1 and number 2. Well, in the case of the spherical orbital, there's only the one spherical orbital. So it's just 0 because there's only one of them. I feel like I should make that into some picture. Sorry, never mind. The one has XYZ, 3 axes, so it's 0, 1, 2. I'm sorry, that's not right. It's 0, 1, minus 1. Negative L to plus L. What's L? L is this number. So if the sublevel quantum number is 0, then the magnetic quantum number can only be 0 because you can't have minus 0 to plus 0. If it's 1, then this would be negative 1, 0, 1. If L is 2, then M would be negative 2, negative 1, 0, 1, 2. And if L is 3, then M, the magnetic quantum number, would be minus 3, minus 2, minus 1, 0, 1, 2, 3. So here's what I said earlier. One orbital is more or less randomly assigned the value of 0. Then the spin quantum number describes an electron's angular momentum. And you say, what in the world is angular momentum? Well, so here's the problem. We've got 2 electrons in an orbital. Electrons are negative. Like charges repel. So why in the world can 2 electrons stay in the same orbital? Why don't they repel each other, or one of them anyway, out? So what we think is, we think that the electrons, okay, these are waves, but it's hard to imagine this as waves. You're going to have to imagine it as a particle, I guess. We imagine that these electrons are spinning kind of like what, a top or the earth or whatever. We imagine that they're spinning in opposite directions. And what that does, if you remember, a moving charge produces a magnetic field around it. So if they're spinning in opposite directions, they would be producing opposite magnetic fields, and opposites attract. So the opposite magnetic fields attract, but the 2 negatives repel, and those 2 different factors cancel each other out, so the electrons can exist in the same orbital. All right, so that's just a lot of foolishness there, I guess. Any questions about any of this? You don't have this. There are things I liked better about Easy Talks, and there are things I like better about Zoom. One of the things I like better about Easy Talks is it actually gave me a timer telling me how long things had been going. All right, just go a few more minutes and then that can be it for today. So just a little bit about the nucleus. The nucleus was discovered by Rutherford, if you remember the atomic models back from chemistry. I know that's asking a lot to remember stuff from a class 2 years ago. But Rutherford bombarded atoms with alpha particles. If you remember, again, okay, so if you cannot hear your voice, select a different microphone. All right, looks like we're good. I don't know what it's talking about. If you can't hear me, let me know. And if you can't hear me, then you wouldn't know that I said let me know. Hopefully, if you can't hear me, you would be letting me know. All right, so our friend Rutherford bombarded atoms with alpha particles. Alpha particles are helium nuclei, 2 protons, and 2 neutrons. And he showed that, well, first of all, let me tell you what happened. So he bombarded this with these, I think he used gold foil. And he bombarded them with alpha particles, and many of the alpha particles went straight through the gold foil. Remember, gold can be pounded so thin that light will pass through. So he had this very, very thin gold. He bombarded it with alpha particles. Some of the alpha particles went through as if there was nothing there, and some of them bounced back as if they'd run into a brick wall. Most of them went through, only a few bounced back. So he figured out, he decided, he showed that most of the mass of the atom was in a very, very small area of the atom, and that is what we now know to be the nucleus. And most of the mass, like 99 point something percent of the mass probably of the nucleus, is in some tiny fraction, 2 or 3 or less percent of the atom. He found that the smallest piece that could be broken off was a proton, so concluded that all atoms contain protons. All nuclei contain protons. Chadwick then discovered neutrons. If you remember, Chadwick's name was, first name was James, so it's probably before your time, but if you remember the cartoon Jimmy Neutron, that's probably about right. All right, I think that'll be enough. This is going to take a little time for composition of the nucleus as we get into all the different parts of it in detail. So I guess that I'll leave it off there for today and see you at 8 o'clock tomorrow. And hopefully in a day or two, all of this will be working a lot more smoothly than it has been so far. Already today is better than yesterday. Any questions? All right, in that case, I will bid you adieu